Hi guys, Mr. John here. Today I'm gonna give you a look inside my scope, and also I'm gonna go and replace few capacitors that I did not replace already. Those are paper capacitors, because it's a shame really, but I did not mark in any way the date when I got this beautiful piece of test equipment, so I don't know exactly when. I don't even remember the year, to be honest, but I remember that shortly after that, about a couple of weeks period, I went and replaced all electrolytic capacitors inside this beast, and since then it was working quite good. But maybe you saw in my previous videos that the input coupling cap is very leaky. The cap which AC couples the input and is shorted by this switch. This switch changes from DC coupling to AC coupling. Right now it is AC coupled. Signal goes through that 100 nanofarad capacitor from this jack to the input amplifier, and when it's pressed, this switch just bypasses it and lets the DC part through to the amplifier as well. One thing I just love about this old test equipment from Soviet Union is it's very easy to take apart. See this screw? You back it off just one turn or one or two turns, same as on the other side. And that screw. And the whole case just splits. This half will just lift off, and so will this bottom half, but of course you need to flip it to do that. Okay, I undid the other side, half a turn, 1.5 turns, it should be enough, and it is. As you can see, it very easy, it holds in place. It pinches that cover with that big washer kind of thing, pinches this to this piece of chassis and holds it in place. And that's the overall look inside. You can see the actual tube, which is shielded. Here you can see some boards. This one is a vertical amplifier, if memory serves me right. Yeah. This one drives vertical deflection plates. As you can see, there are wires from this board directly into the tube. This one is a horizontal plates driver, goes to the plates as well. This one is a main power transformer. This beast is a regular frequency 50 Hz transformer. As you can see there, multiple taps. It's a toroid in a shielded case and potted. Good luck finding a replacement for that if it goes. This thing is also a transformer, just like the other one, but this one is a ferrite core transformer, also in this shielded case and potted. And why is it so? Because this scope actually has there is a possibility to power the entire device from 24 volts DC. This thing really produces a couple of voltages, quite a few. But also those voltages can be easily obtained by just feeding 24 volts DC into the DC to DC converter, a push-pull converter that drives this transformer, and that's actually what produces all the voltages. It is actually used in normal operation as well. This transformer steps down the voltage, then it gets rectified, smoothed, fed into that converter, and then this beast provides the rest of the stuff, of the power. And the capacitors I want to replace are these kind of things. You can see 0.05 microfarads plus minus 10%, 160 volts, dated to October 1981. These are paper capacitors. They may look like they are sealed, but I did see quite a few of these style capacitors going bad anyway, so I will replace those. These are not that notorious to fail, as you can see, because they are quite sealed there. The other type, which is very notorious to fail, I will show you when I flip the device. But before I do that, I'm gonna show you what this is. This is a delay line. Sometimes it is just a very large T filter network, just multiple inductors and capacitors. In this case, they really did delay line in a very simple way. They just packed lots and lots of wire in this coil. That's it. If you take a peek inside, you may be able to see the wire. Or not, because the phone is super dumb. It's a dumb phone, not a smartphone, but a dumb phone. Oh, come on! Hopeless. Absolutely hopeless. Anyway, it contains just a bunch of wire. Maybe you'll be able to see it from this side. Oh, finally! You can see it's a spiral. It's spiraled wire, then that spiral is spiraled again. Basically, it contains a couple of tens of meters of that wire in Teflon insulation. This is your vertical sensitivity switch. There are some trim caps to adjust the response on the divider ranges. This is a time-based control. Now, there are some capacitors that just don't require to be changed, and those are these tubular ceramics. They are just fine. So are these trim pots. Another type of capacitor that I really like is this style. Let me show you on the other side. This kind of capacitor. As you can see, this brown thing. This is a mica capacitor. I don't know if they are silver mica, but they definitely use mica as an insulator, as a dielectric there. These are very stable. They are sealed, so they don't, I did not hear of any of them to develop silver mica disease like the open ones do in an old American radios. So that's it. And this capacitor, I don't quite remember what it does, but judging by the look of it, it is an oil-filled capacitor. And I don't want to touch it because it probably holds quite a lot of voltage still. And there you can see replacement capacitors that I tacked in. You can also see some capacitors that I tacked in there, because those old capacitors, they look like this. You can see they are big. They have a thread there and a nut, and they are pinched against the chassis, and that's the negative contact and the mechanical fixing. Whatever, you understand what I mean. It fixes it robustly to the enclosure and also provides a electrical contact. I could have restuffed them with modern capacitors, because modern capacitors are so much smaller, but nah, I did not decide to do that. Anyway, let's flip it on the other side and see quite a bit more components that are on the other side. As you can see solder side now, but no components yet. And here we go. Right here, let's start from this side. We have this board. That's a power supply board. It holds it holds a bridge, couple of rectifier diodes, a regulator transistor there, a trim pot to adjust the voltage there, It's a Zener diode in this package. Let me get something to point with. That's a Zener diode actually. And that's a capacitors again that I want to replace, but they are in a power supply. They are just a decoupling capacitors, not very critical. There is another one hidden in this tubing, but that's pretty much the same value as this one. I checked by schematic. You can see I replaced a couple of capacitors here, quite a few. They are obviously, they were much bigger, as you will probably see by the little bit of residue there. You can kind of see a circle like that, and even the pin pitch does not match, so I had to just bend one lead and fix it this way. This, well, I think it's bloody obvious what it is. It's a multiplier. If memory serves me right, it's a tripler. I don't remember for sure. And it is actually looks quite crikey. As you can see, the casing is just meshed up and stuff, but that doesn't really matter, to be honest, because this thing is potted with a really soft compound, I have to say. Let me show you that it is not a hard resin, but a soft compound. I don't know if you'll be able to see it. Let me just flip it to the sunlight. Okay, hopefully you'll be able to see it now. You can see it is quite smooshy. Rather soft resin. There are some... Boy, it is inconvenient. Oh man. I know that it is inconvenient for you to watch this handheld footage, but for me it's even worse. Try lugging it around and then complain about it. Oh boy. You may be able to see some components down there. You're probably just about able to see a black kind of rubber seal there, a lead going there, and then an aluminum rim. That is a paper capacitor to be. Again, in the multiplier. Thank you very much, but my only hope about it is that it is still good is because it is potted. And when it's potted, it is airtight seal, and air can't get in and break down the paper, so it will not get conductive. I hope. I hope it's god damn it, what it is? It's an air leakage that makes them leaky. If they are sealed completely airtight, they should be fine still. And another, remember I told you that I don't care about this outer shell because this thing is potted solid. This outer shell is really needed only when you actually fill the thing with a compound, so it holds its shape when it cures. Now it doesn't really need it, so it's not a big deal. Moving on. Here we have a board which is a vertical amplifier board. And this has a little shield with a lightning strike on it, a bolt, thunderbolt, whatever you like to call this. And this shield covers these two controls, which are focus and brightness, because they have quite a high voltage on them. So that's why you see this shield here. And right here you can see this kind of weird construction where they have these Teflon standoffs that raise above the board and then have these kind of cups where the actual component leads are soldered. So it actually is this way. the BNC there, as you can see. Again, you don't see a squat. Oh, that's just amazing. What an amazing review. So that's a BNC right there from the other side. As you can see, the center contact goes to this 27 ohm resistor. Then it goes to that switch. This switch, which is AC-DC coupling. Then there is 7.5 picofarad capacitors to chassis from the node. Then that goes through the capacitor if it's AC coupled. Then the other lead of the and the switch just bypasses it when necessary. This capacitor, I mean, and that's that leaky input capacitor that I was talking about. As you can see, this is not really all that sealed. This has this rubber seal, which is notorious to get leaky, and the rubber just hardens with time, shrinks, lets the air in, and paper goes acidic, capacitor goes leaky. I won't be surprised if this capacitor is really now pretty damn leaky. Then the other side of this capacitor, of the end the switch, because they're in parallel, goes over here through the hole in the board, and again you don't see a squat. That's just amazing. Okay, you can see that wire going through the hole in the board over here to this cup. Then there is this resistor, which is 1 meg resistor to chassis, to common point, which is your input impedance. Then there is a 100k resistor, which is with 10 nanofarads ceramic capacitor across it, this guy. It goes to this cup. Then there is 180 ohm resistor that goes to this cup, where you can see a couple of diodes soldered here. One diode is soldered with its cathode to that point, another diode is soldered with its anode to that point. You can see they actually have their symbol on there, and those diodes are actually then soldered on the board to these two diodes, and they're all in series. So that's cathode, anode connected to this cathode, and same here, anode, cathode connected to this anode. Again you can see actual symbols there. They are in series, and they are protection diodes. Then there is this metal can transistor, which is a JFET. That's your very input. That's a source follower to make sure that you don't load up whatever circuit you're measuring. The gate of that JFET goes to this cup, and the other source and drain is actually are actually on the board, as you can see there. Then there are a bunch of other stages which are actually built on germanium transistors. These UFO style transistors are actually all germanium, these big ones. Silicon ones are these small things. That's actually a capacitor. At least I think it is. Anyway, so you can see quite a lot of stuff on it. Another interesting thing on this board is this package, which, as you can see, it's a multi-pin package, and this is just an operational amplifier in a metal can package, as you can see. This, by the way, is another mica capacitor there. It's quite good. Now to this board. That's your vertical amplifier board. That's your sweep board. Sweep, trigger, hold off, all that stuff connected with horizontal. Let me actually take a sip, because it is very... My hands are tired already, and the video is gonna be very shaky that way. On this board you can see a couple of good capacitors here. Those mica capacitors I was talking about. But there are also a couple of these paper capacitors which go nasty over time. And this one, 100 nanofards, 160 volt rated ones, is connected directly to a device which is very, very weird by today's standards. This is a tunnel diode. This is a main device that the triggering circuit of this scope is built around. That's your tunnel diode. There are actually another one right there, but this one does not have any paper caps near it. These devices are actually hard to find, and even if I manage to find them, in case it goes bad, there is this beautiful thing about it that it is quite it is made, the same part number is made in modifications like ABCD kind of things, and they differ a little bit from each other by parameters. And even if I buy the exactly one, let's say it is a D modification, there will still be a need for me to adjust some bias points of these two transistors and adjust some values around it to make it work right. So I do not just want to go and damage this tunnel diode anyway. So I will replace this capacitor in a rather crikey fashion. I'm gonna go cut off this lead, and I'm gonna solder the new capacitor to that lead, and the other side is gonna solder directly into the board. I don't really have anything sensitive on this side, so I'll do that here, direct solder job. Whether here, where this lead is connected directly to this lead, I will actually clip it off here and solder the new capacitor right here to minimize the thermal stress on this device, which is again very hard to find and very crikey to get the scope going again, especially if that's your only scope, because to tune it right you need another scope. Alright, funny. So that's that kinda on this side. There is another capacitor which gets leaky, but this is not really a big problem. It is somewhat like a decoupling capacitor, not a big deal. I will change this capacitor definitely because it's input coupling and it's very bad. And the memory on my phone goes kind of runs out, so I'm gonna stop it here and then clip off these capacitors and show you that they are indeed leaky. That capacitor which is connected really close to the tunnel diode is connected to transistor tester. Let's see what it has to say. Oh, look at that! It says that it is 227 nanofarads, but it is rated 100. You know what? It is leaky. It's a dead giveaway. You can see ASR. And you can see V loss 4%. 4% may not sound like much, but it's a huge amount. A good capacitor should be sub 1% V loss. And another dead sign that you can see again, 220 nanofarads. I mean, like, come on. The capacitor is rated 100 nanofarads. Of course it's leaky. These devices that measure capacitance by charging and discharging them are very sensitive to leaky capacitors. And if you measure a capacitor which is rated 100 and it shows anything else than 100, and it shows more than 100, you know for sure that that capacitor is leaky. There is no other way around it. It's just the way it is. And as for getting to that capacitor, it is quite crikey. It is very buried there, but I will get it out anyway. Okay, the capacitor is removed. That one was there. Here it is. This seems like a heat shrink, but it's not. It is very hard plastic by now. Some of the markings is actually made their way on there. If this stupid device will even focus on it. As you can see there. But they're still visible here. 0.1 microfarad, plus minus 10%, 500 volts. This is a gross overkill. You can put 100-volt capacitors there, it will be fine. There is 6 divisions, 6 vertical divisions, and the maximum sensitivity is, well, the worst sensitivity really in this case is 10 volts a division. So we have 60 volts peak to peak there. There is no point to feed more than that, because it will go off the screen. Alright? Makes sense, isn't it? Doesn't it? So, this one dates to August of 1981. Let's take a look how much this one will say. Make your bets, ladies and gentlemen. I make mine at about 300-400 nanofarads. Oh, okay. That's not what I expected, but it is 2%, which is way more than it should be. I'm actually kinda tempted to replace it with a bigger value. That should actually go, what it should do is that should improve the frequency response. It should catch on earlier. I mean, like in the AC coupled mode, it should see a frequencies which is lower, because this like 10 Hertz won't go really well through this thing, through this 100 nanofarads. It should go much better through 470 nanofarads, for example. This one is actually rated even more. Oh, this is 330 nanofarads. Anyway, you can see it. 630 volts. Nice device. I do have a replacement like this. 100 nanofarads. 104. You can see 400 volt. Very small, but I'm gonna go and use this instead of that bastard. Again, I'm gonna solder one leg to the cutoff lead there that still sticks out, and the other side will be soldered directly into the board, because I just don't want to risk it. And there is a 417 nanofarads. You can see they're very similar to 330. Same kind of styling, as you can see. Just a minor size difference. I don't know, maybe I'll put 330. I have to think about it. Yeah. Okay, picked few capacitors. For the input I'm gonna use 470 nanofarads. You can see there. For those two, this one and this one, I'm gonna use 100 nanofarads each, these kind of devices. By the way, you may wonder why it is... Let me kill the damn fly. In case you think that I'm joking, no, I'm not. Anyway, moving on. In case you're wondering why they are rated 160 volts, well, that's because I did not see any capacitors of this style being rated less than that. I think that's a minimum voltage rating that these capacitors were manufactured. Yeah. And just so you see the difference, I'm gonna go and put this 470 nanofarads on the transistor tester, and you will see how different it is in comparison to that leaky bastard. Come on! 460 nanofarads. You can see SR is just bizarre. Less than 100 milliohms. And the leakage is 0.1%. See? As for these 100 nanofarads, sub 1 ohm ESR, nice capacitance, and the leakage won't be displayed because the leakage is displayed for capacitors larger than 150 nanofarads, I think. I can actually cheat and add 2 in parallel, but what's the point of that? Oh no, you can see 0.3, it's fine. And the other 100 nanofarads, again quite good. Good capacitance, sub 1 ohm ESR. The leakage is 0.1. Awesome. Big difference. So let me do just that. I won't really go and show you the actual soldering because it's kind of boring. One thing I'm gonna show you though is how amazing this thing is to repair. And what do I mean under that? Well, that's this board we are interested in. So we go take our flat-bladed screwdriver, undo a couple of screws, these are long bastards. Okay, enough. So you undo those screws and they actually don't pop out all the way, because you will see why. And look at this. Isn't it amazing? I mean, like, it's so freaking convenient to repair these things. It's ridiculous. And why do they don't pop out? Well, again, handheld footage. As you can see, this screw is the threads on it are quite larger than the hole in that washer, so it does not pop out. You can actually kind of hold the washer with pliers and unscrew it, but what's the point in that? It's kind of handy. Make sure that you don't lose it. Soldering is just so not the best, but not the worst. Yeah. And if you flip this open, you can see some of my horrific replacement of the capacitors there. And also you can see another capacitor right there, which is a paper capacitor again, and this bastard, which is rated 1000 volts, 10 nanofarads. I might actually discharge this bastard first, desolder one leg, test it. If it's bad, I'm gonna replace it anyway. But if it's good, I'm gonna leave it alone, because this one seems to be sealed pretty well. You can see the side of it right there. It is a kind of glass seal thing, so maybe it's still fine. That. I decided to bite the bullet and yeah, soldered it right in. Try to keep the dwell time as short as possible. Another one is not big deal. And I also changed that capacitor there. It was quite leaky. This one I measured it and the value of it was 9700 picofarads, which is a little bit less than its rated value, so it's not leaky. I'm not too bothered about that. It is kind of wrong, because you should really test the leakage with a dedicated instrument that applies a rated voltage, 1000 volts in this case, but oh well. I cannot believe that this capacitor will be fine, this bastard, because it is sealed pretty good. Maybe it is an oil field as well. It's not that nasty serious capacitor anyway, so yeah. Now I'm gonna go and gonna go and screw this in. Oh, we'll go and fix this kind of blob of flux there first. I'm gonna put it in, then probably gonna replace. Oh, I will have to put the AC coupling cap still, because I did not do that yet. But that's it so far. Okay, so I soldered the input AC coupling cap there in slightly different fashions than the other one was soldered, but to exactly same place in the circuit as it was the other one. Anyway, I also found a capacitor which is somewhat critical on this board. This one goes from the base to pretty much collector of this transistor, so if it goes leaky it will throw off this regulator. So I replaced that. These ones are just a decoupling capacitors. I couldn't be bothered really. Maybe I'll replace them later with ceramics. Speaking of ceramics, remember that this scope whines like crazy. And the thing is that the transformer there, as you can see, that switching transformer is potted solid. So what can whine? Maybe this. It's a big ass ceramic disc capacitors. Depending on their construction, they can be pretty much a piezo transducers. And judging from the size of this capacitor, I pretty much expect it to emit some noise. I don't know. Maybe I will go actually and replace it with a film capacitor. I do have a 10 nanofarad 1 kilovolt capacitor to replace this with. This one says 1.6 kV, but it won't see that in operation. Again, these capacitors are just manufactured like this, in these kind of values. This, by the way, goes from one end of the filament of the tube to chassis ground. I guess it kinda AC couples it to chassis, so that node is pretty much at 0 volts and won't emit some noise into the beam. Anyway, so that's that. I'm gonna turn it on, I'm gonna put my ear to it, and I think I know that is what emits some noise. Because the transformer again is potted solid, it couldn't be that. First of all, I'm gonna turn it on and see, didn't I muck around, didn't I kill that tunnel diode by soldering the capacitor near it. I kept the dwell time really short. I hope I did not do anything dumb. Oh, yeah, that would suck. Okay, piezoelectric transducer is removed, and when I turn it on, it still whines like crazy, because the problem is not only in that place. After removing that capacitor, the noise did not quiet down in this section, but it's still quite wild in this section, and that is because in the multiplier inside, god damn it, this stupid son. Inside of the multiplier there is a capacitor like that. You can see it right there. See that orange disc? And there is another one there. And it's completely potted with resin, and that doesn't help a squat, unfortunately. Awesome. By the way, I replaced this 10 nanofarad capacitor with a 7.2 nanofarad 1600 volts as well. I don't know, I may just leave this one out. It works fine with that one. Oh, crap. What can I say?